So this is lesson 2 of unit 12, and what we're going to talk about today is kind of an application of acid-base reactions, and that application is called a titration. And so our goals for today is we want to be able to explain kind of the purpose of a titration, how to perform one. We want to be able to identify the equivalence point on a titration curve. And then finally, calculate the molarity of an unknown acid or base by performing a titration. And so this is kind of your notes portion that's kind of fill in the blank. And so whatever is bolded and underlined is what will go in the blanks there. So the entire purpose of this thing called a titration is to determine the concentration of an unknown substance by reacting it with another substance of a known concentration. So let's pretend that maybe a chemical company, maybe accidentally, has a spill, and they want to bring in someone to kind of test and see how concentrated is it. Or for example, like us, when we store our chemicals, if a chemical has been on the shelf for a long time, we may want to test it to see if it still has the same concentration that it says on the bottle, or if that concentration has weakened over time. But essentially what we're doing is we have something that is unknown in concentration, and we're going to test it to determine how concentrated it actually is, okay? And so the way we'll determine that is by taking the unknown and reacting it with something that is known. So we're going to have two main chemicals involved, one that's unknown, one that's known. Now, when you're doing this process with acids and bases, this takes advantage of the neutralization process. And so when you neutralize an acid with a base, you typically form salt water. Now, the salt can kind of vary. The salt is just any ionic compound. It doesn't have to be sodium chloride. And then water is consistent. That's always H2O. Now, in the example, we're kind of going to use, in this case, we are going to form salt, NaCl, but that's because we're taking hydrochloric acid and reacting it with sodium hydroxide. It's double replacement, so the ions swap, and you end up with sodium chloride and water. And so that's why it's neutralized, is because you're just left with water and then an ionic compound. So when it's neutral, it should be around a pH of 7. Now, there's a few pieces of specialized equipment that are used during a titration. So let's run through those really quickly. So up top, it kind of looks like a very long graduated cylinder, but this is what's called a burette, all right? Now, the burette is specifically designed to allow you to drain a solution kind of from the bottom. And so it has attached to the side a little piece of plastic that's called a stopcock. And the stopcock, when you twist it, it allows some of the liquid to drip out of the bottom of the burette. When the stopcock is parallel to the burette, that means it's open and stuff is coming out. If you turn it so that it's perpendicular to the burette, that will close it off and keep the liquid inside. Now, the flask at the bottom, this is specifically called an Erlenmeyer flask. And the reason this is a good choice for titration instead of a beaker is because it helps kind of prevent the liquid from the burette from kind of splashing up on the sides, and it helps it to kind of roll back down into that bottom portion so that all the liquid is contained in one nice spot. All right. Now, right quick, kind of a few more terms to add in here. So whatever substance goes in the flask is what's going to be called the analyte. And that is the substance that is unknown in terms of concentration. And so we're going to be analyzing it to find out what that concentration is. Now, the substance that is inside the burette, on the other hand, is going to be called the titrant. Okay? The titrant is whatever substance is known, and it's what we will use to perform the titration on the unknown analyte. Okay? So the titrant goes in the burette up top, the analyte goes in the flask on the bottom. Now there's typically one more chemical that's involved, and it happens to be in the flask, and that is an indicator. And so what an indicator does is it will change color when your kind of reaction has completed and once your base and acid have been neutralized. So you'll typically have an indicator in the bottom to kind of change color and let you know when things are finished. All right. So the results that you typically get from an experiment like this are called a titration curve. And the two main parts to take note of are what's on your x and your y axes. So on your x-axis, you have the volume of titrant added. And so what you're measuring during a titration is how much of the stuff from the burette you have to drop in to actually neutralize the substance at the bottom, okay? Now the second thing that you keep track of is the pH of the analyte solution. So for the analyte, we're keeping track of pH, and for the titrant, we're keeping track of volume, all right? Now the volume of the analyte you'll know from the beginning. So I'll call this, so you'll want to know the initial volume of the analyte. But the main things we're reading throughout the experiment are the pH of the analyte, and then the volume added from the titrant. Now in this specific example, what we have is at the bottom, we have an unknown acid, HCl, being titrated by a known concentration of base, NaOH. So at first, when you're measuring the pH of your analyte, the pH is going to start out being low because it's an acid. But if you continue dropping in base, the pH is going to start to raise, all right? And so as the pH raises, it kind of forms this S-shaped graph. All right, and so your graph will level out at a high basic pH if you continue adding the base throughout the titration. And so what we'll notice is that there's kind of a special point right in the middle of this curve that's called the equivalence point. And so the equivalence point is the point at which the number of moles of acid is equal to the number of moles of base. Okay? So again, equivalent is another word for being equal. And so at that point, the moles of our acid is going to be equal to the moles of base. And so that will be the point at which everything is neutralized. And it typically falls kind of right there in the middle of your pH graph. Now, here's the idea. How can we know, when that equivalence point has been reached, when our moles of acid are equal to the moles of base? So we can't get down, with our magnifying glass and count and say, oh, we have 10 acid molecules and 10 base molecules, they're equal. That won't work because they're way too small. So that's where our indicator comes into play. And what the indicator does is it shows us the end point of the reaction, which is an estimation of where that point of equivalence actually is. And so typically an indicator that's used in acid-base titrations is called phenolphthalein. And what it does is right after the equivalence point, it turns a light shade of pink, okay? And so that's kind of this example on the left. And what you're looking for is that pink to kind of stay persistent. You want it to be a light color, but you want it not to disappear as you're swirling the flask. And so that lets you know, okay, I need to stop. I've reached just right past the equivalence point. Now, if you add too much base, your indicator is going to change to a bright, like fuchsia pink, and that means that you have gone too far. You have overshot your equivalence point. Okay? All right. So now what we're going to do before we get you going on the lab is we're going to talk about kind of how you can use your experimental data to actually calculate what the concentration of the unknown substance is. And so we've already kind of established that at the equivalence point, kind of the key realization is that our number of moles of acid should be equal to our number of moles of base. And so we've actually already introduced a formula from the solutions unit where the moles of one thing was equal to the moles kind of on the right side as well. So we had moles equal to moles. And what that formula was, back in our solutions unit, was M1V1 equals M2V2. That was the formula for dilution. And so what we assumed there is that the moles of what we started with were equal to the moles of what we ended with, because in dilution, you do not change the number of moles of your solute, you just add more liters of your solvent to make the concentration weaker. So we're going to take that general formula and kind of use that as our baseline for titrations. And so the formula for titration that we're going to use is, here's kind of the similar part, the M's and the V's, if you will. But instead of 1 and 2, we're going to use A's for acids and B's for bases. So M of A, this is the molarity or the concentration of acid. The VA is the volume of your acid. And then this little BA, this is going to be something that says the number of acidic parts. And then this just repeats on the base side. So the B subscript B is the number of basic parts. The MB is the molarity or concentration of your base. And the VB is the volume or the liters of your base as well. All right, so let's do a few little practice calculations to show you how this works. So this says determine the volume of 0.100 molar NaOH needed to titrate 10 milliliters of 0.1 molar HCl. So they're telling us kind of our starting conditions for our titration. We are using the base to titrate 10 milliliters of 0.100 molar acid. They tell us that our base has a concentration of 0.100 molar, and they're asking us to find the volume. Okay, so if we write out our formula, we have BAMAVA equal to BBMB VB. Lots of B's there. All right. So what we'll do is we'll kind of go and plug in what we know. So our molarity of acid, normally that's what we'll be solving for, but in this case they tell us that it's 0.100 molar. So we'll go ahead and pencil that in. They tell us that the volume of acid in our flask is 10 molar. So we'll go ahead and pencil that in as well. Or it's not 10 molar, 10 milliliters. Sorry about that. All right, we're saving the B spots for now. Now they tell us our molarity of base is 0.100 molar. And finally, the volume of the base is what we're looking for. So that will be what we're solving for, the volume of the base. Now, right quick, let's talk about these little B's and look at what they mean. So the BA is the number of acidic parts within the acid. So if we remind ourselves, the acidic portion is the hydrogen and the basic portion is the hydroxide. So if we take a look at our acid, hydrochloric acid, it just has one acidic part, one hydrogen. So our B of A is going to be 1. If we look at our base, on the other hand, there's just one basic part, one OH. And so it'll be a 1-to-1 acid to base relationship. So now we just do a little algebra to get it solved. So we'll multiply all of these things together on the left. So 0.1 times 10 times 1, which gets us a nice answer of 1 there. And then we'll do 1 times 0.1 on the left, or on the right rather. So that's 0.1, and then we've still got our VB in place. And so then what we'll do to get VB by itself is divide both sides by the 0.1. And that tells us that 1 divided by 0.1 is 10 milliliters. So our VB is equal to 10 milliliters. All right. And so what that tells us is that it will take 10 milliliters of the base to be dispensed in order to neutralize that acid that's in the flask. All right, so let's go try another one right quick. So calculation number 2, and this is kind of more realistic for a titration. So what they tell us is that we have 50 mils of unknown hydrochloric acid. So this will be the volume of the acid, but since it's unknown, we'll be solving for the molarity of the acid. Then what they tell us about our base is that it took 100 milliliters of 0.3 molar NaOH to titrate it. So this is the volume of the base that we had to release, and its concentration was 0.3 molar. So let's go ahead and write out our equation. So BaMaVa is equal to BbMbVb. All right, so let's start with what we know. So let's look at our acid and see how many acidic hydrogens it has. It just has one acidic hydrogen. The molarity of acid is unknown, so that's what we'll be solving for. The volume of acid, they told us that we started with 50 milliliters in our flask. Now, let's look at our Bb, our number of basic parts. We have one hydroxide there, so our Bb will be 1. Our molarity of base was 0.3 molar, and our volume of base was 100 milliliters. Okay, so go ahead again and multiply everything on that right side. 0.3 times 100 times 1, that should get us 30. And then on the left side as well, we've still got Ma, and then 50 times 1, of course, is still just 50 there. Then we'll go ahead and divide both sides by 50. So 30 divided by 50 gives us 0.6. So the molarity of acid is 0.6 molar. And so it took twice as much base to titrate the acid, so it makes sense that it would be twice as strong as our base was. So our acid is 0.6 molar, and it took 100 milliliters of 0.3 molar NaOH to titrate it. Now, last problem, let's do one more of these just for practice. So here we're changing up our acid. Instead of HCl, we're going to use sulfuric acid. And so it says, determine the concentration of 25 mils of unknown sulfuric acid. So we're going to be looking for the molarity of our acid. And we know that we started out with about 25 milliliters of it in our flask. So that's our volume. Now our base, they've changed our base on us to calcium hydroxide. And for our base, we had to dispense 53 milliliters of it. And it had a starting concentration of 1.5 molar. So we'll go ahead and write out our formula. So BaMaVa is equal to BbMbVb. And so let's fill in what we know. So we'll start off with the acidic portion. So what's different about sulfuric acid is it has 2 acidic parts. It can donate 2 hydrogens, so that's going to make our Ba2. The molarity of the acid is what is unknown, so we'll just keep that as a variable. And we were told that we started with 25 milliliters of acid in our flask. So now for our Bb, if we look at our base, it also has 2 hydroxides, so our Bb will be 2. The molarity of the base was 1.5 molar, and the volume of the base was 53 milliliters. So again, we'll go ahead and multiply everything together on the right. 2 times 1.5 times 53. What that gets us is 159. We'll do our multiplication on the left. 2 times 25 gets us 50. Then we'll go ahead and divide at the end. Okay, so Ma equals 159 divided by 50. And that gets us a molarity of 3.2 molar. So in this case, our acid was stronger in concentration than our base. And so this is normally your end result of your titration, is that you want to be able to determine whatever the concentration is of your analyte. All right. So I think, oh yep, one more slide I wanted to show you. So what we've kind of selected as the activity for today is kind of a virtual titration lab. This one is put on by a program called Labster, and it's supposed to be more interactive. Sometimes the graphics and little things are a little weird. You'll see what I'm talking about. But hopefully it'll be something just a little different that can help you get a little bit more of a lab feel. But one thing I wanted to point out about this setup is that the markings on the burette can sometimes be a little tricky. So because the burette is designed to dispense like liquid downward, the way the markings read is they increase as you go down. So notice this is marked at 20, this is marked at 21. And so what that means is you want to read at the meniscus. So here is my dip, this is my meniscus. So what this means is my starting volume is 20 milliliters. But let's say that my meniscus lowered all the way to maybe here, okay? So what you have to be careful of is this is not, this little mark right here is not 21.1. Instead, you start at 20 here, and this becomes 20.1, 20.2, 20.3, 20.4, 20.5. And so everything between this line is greater than 20, but less than 21. Then starting at the 21 line, that's where it would go 21.1, 21.2, kind of so on and so forth. So just be careful as you're reading that you're making sure to make the correct measurement. So for example, this would be 20.5 instead of 21.5. And then last thing on sig figs, because a burette reads to the tenths place, that makes it a very precise tool. So whenever you're taking a reading from a burette, you'll want to record your values to the hundredths place. So instead of saying 21.0, it'd be 21.00, or if we were saying 20.3, 20.32, you just want to make sure to have at least 2 decimal places there. All right. But again, in the lab, you'll have your burette up top with the titrant. You'll have your flask down in the bottom with the analyte. And I think they're going to be having you all in the lab kind of help with an acid spill, I think. So, all right. So good luck. Thanks for listening to a little bit about titrations.